Understanding Physics, 3 volumes in 1, by Isaac Asimov. Read, recorded, and produced by JohnLothe. Chapter 11. Sound. Water waves. Fluids can move in the various fashions that solids can move. They can undergo translational motion, as when rivers flow or winds blow. They can undergo rotational motion, as in whirlpools and tornadoes. Finally, they can undergo vibrational motion. It is the last that concerns us now, for a vibration can produce a distortion in shape that will travel outward. Such a moving shape distortion is called a wave. While waves are produced in solids, they are most clearly visible and noticeable on the surface of a liquid. It is in connection with water surfaces, indeed, that early man first grew aware of waves. If a stone is dropped into the middle of a quiet stretch of water, the weight of the stone pushes down on the water with which it comes into contact, and a depression is created. Water is virtually incompressible, so room must be made for the water that is pushed downward. This can only be done by raising the water in the immediate neighborhood of the fallen stone, so the central depression is surrounded by a ring of raised water. The ring of raised water falls back under the pull of gravity, and its weight acts like the original weight of the stone. It pushes the water underneath downward and throws up a wider ring of water a bit further away from the original center of disturbance. This continues, and the ring of upraised water moves farther and farther out from the center. As it moves outward, the total mass of upraised water must be spread out through a larger and larger circumference, and the height of the upraised ring is therefore lower and lower. Nor is there a single wave emanating from the center of the disturbance. As the initial wall of upraised water immediately about the center of disturbance comes down, it not only pushes up a wall of water beyond itself, but also pushes up the water at the center. This rises and then drops again, acting, so to speak, like a second stone, and setting up a second circular wall of water that spreads outward inside the first wall. This is followed by a third wall, and so on. Each successive wall is lower than the one before, since with each rise and fall of water, some of the energy is consumed in overcoming the internal friction of the water and is converted into heat. As a particular wall of water spreads outward, some of its energy is also being continually converted into heat. Eventually, all the waves die out and the pool is quiet again. However, it is very slightly warmer for having absorbed the kinetic energy of the falling stone. To produce a wave, then, we need an initial disturbance. If this initial disturbance, in correcting itself, disturbs a neighboring region in a fashion similar to the original disturbance, the wave is propagated. In a propagated wave, if we concentrate our attention on a given point in space, we see that some property waxes and wanes, often periodically. In the case of water waves, for instance, if we view one portion of the water's surface and no other, then the varying property is potential energy, as that portion of the surface first rises, then falls, then rises again. It is important to realize that the water is moving up and down only. The disturbance is propagated outward across the surface of the water, and it appears to the casual observer that water is moving outward. However, it is not. Only the disturbance is. A chip of wood floating on water that has been disturbed into ripples will rise and fall with the rise and fall of the water it rests on, but the moving ripples will not carry the wood with it. To be sure, waves approaching the shore will carry material with them, sometimes even forcefully, as the water dashes on the rocks or beach. These waves, however, are being driven by the horizontal force of the wind and are different from the ripples set up by the vertical force of a falling stone. Suppose we imagine a cross-section of the surface of the water that is undergoing the disturbance of a falling stone. Ideally, ignoring loss of height with increasing circumference or loss of energy as heat, we have a steady rise and fall. This rise and fall is what we commonly think of when the word wave is spoken, or when we speak of a wavy line. In its simplest form, such a wavy line is identical with the type of curve produced if one plots the value of the sine of an angle, see page 111, on graph paper as the size of the angle increases steadily. For an angle of 0 degrees, the sine is 0. As the angle increases, the sine also increases, first quickly, then more and more slowly, till it skims a maximum of 1 at 90 degrees. For still larger angles, it begins to decrease, first slowly, then more and more rapidly, reaching 0 again at 180 degrees, and passing into negative values thereafter. It skims a minimum of -1 at 270 degrees, then increases again to reach 0 once more at 360 degrees. An angle of 360 can be considered equivalent to one of 0 degrees, so the whole process can be viewed as beginning again and continuing onward indefinitely. In plotting the graph, then, one gets a wave-like figure that can extend outward forever as it oscillates regularly between +1 and -1. It is this wave-like figure, the sine curve, that represents the shape of an idealized water wave. A wave like the water wave, in which the motion of each part is in one direction, up and down in this case, and the direction of propagation of the disturbance is at right angles to that direction, outward across the water's surface in this case, is a transverse wave. Transverse is from Latin words meaning lying across. The motion of the water itself lies across the line of propagation. The point at which the disturbance is greatest, in the upward direction, +1, in the sine curve, is the crest, and the point at which it is greatest in the downward direction, -1 in the sine curve, is the trough. Between crest and trough are points where the water is momentarily at the level it would be at if the surface were undisturbed. 0 in the sine curve. These are nodes. There are two kinds of nodes in these water waves. For water may pass through a node on its way down to a trough, or on its way up to a crest. We might distinguish these as descending nodes and ascending nodes, borrowing terms that are used in astronomy for an analogous purpose. The vertical distance from a node to either a crest or a trough is the amplitude of the wave. Two or more points that occupy the same relative positions in the sine curve are said to be in phase. For instance, the points on the various crests are all in phase. So are the points on the various troughs. The ascending nodes are all in phase. The descending nodes are all in phase. All points lying a fixed portion of the way between an ascending node and a crest are in phase, and so on. If two waves exist, and if they match up in such a way that the crest of one is even in space or form with the crest of another at the same instant in time, these portions of the two waves are said to be in phase. It is possible that the entire stretch of both waves may be in phase in this fashion, crest for crest, and trough for trough. Naturally, points on a single wave that are not in phase are out of phase, and a pair of waves in which the crest of one case does not appear at the same time as the crest of another are out of phase. A sine curve can be looked upon as consisting of a particular small portion that repeats itself indefinitely. For instance, a portion of the sine curve from one crest to the next can be shaped into a stamp, if you like, and the entire sine curve can be reproduced by stamping that one crest-to-crest portion. Then another like it to its right, another like it to the right again, and so on. The same could be done if we took a portion of the sine curve from trough to trough, or from ascending node to ascending node, or from descending node to descending node, and so on. An appropriate stamp can be made covering the section from any point on the sine curve to the next point in phase. The length from any such point to the next is constant for any particular sine curve. This length, let us say from crest to crest for simplicity's sake, defines a wavelength. The wavelength is usually symbolized by the Greek letter lambda. If nodes are not distinguished from each other, and they are usually not in physics, then successive antinodes are half a wavelength apart. A particular crest moves outward along the surface of the water, though the water itself, I repeat, does not move outward with it, and the distance it travels in 1 second is the velocity of the wave. Let us suppose that the velocity of a particular wave is 10 meters per second, and that the wavelength, that is, the distance from crest to crest, is 2 meters. If we fix our attention on a certain point of the water's surface, we will note that a particular crest is at that point. It travels outward, and 2 meters after it, a second crest occupies that point. 2 meters after that, there is a third crest, and so on. After 1 second, the original crest is 10 meters away, and a fifth crest, 10 divided by 2, is occupying the original spot. The number of crests, or the number of troughs, ascending nodes, descending nodes, or any successive points in phase, passing a given point in 1 second is the frequency of the wave. Frequency is usually symbolized by the Greek letter nu. From what I have said, it should be clear that the velocity of a wave divided by its wavelength is equal to its frequency. So, nu equals v divided by lambda, equation 11-1. The units of frequency are therefore m divided by second divided by m, or 1 divided by second. Since in algebra 1 divided by a is said to be the reciprocal of a, 1 divided by second is sometimes spoken of as reciprocal seconds. More often it is referred to by the phrase per second. The frequency of the waves mentioned above as an example can be written 5 divided by second, and this can be read as 5 per second, or as 5 reciprocal seconds. Sound waves. At a comparatively early stage in the quest for knowledge, sound came to be thought of as resulting from a kind of wave motion. The first experiments on sound were conducted by the ancient Greeks, and these were rather remarkable in one way, for the study of sound was one branch of physics in which the Greeks seemed, by modern criteria, to start off in the right direction from the very beginning. As early as the 6th century BC, Pythagoras of Samos was studying the sound produced by plucked strings. It could be seen that a string vibrated when plucked. The plucked string's motion was only a blur, but even so, certain facts about that blur could be associated with sound. The width of the blurred motion seemed to correspond to the loudness of the sound. As the vibration died down and the blur narrowed, the sound grew softer. And when the vibration stopped, either by natural slowing or by the abrupt touch of the hand, so did the sound. Furthermore, it could be made out that shorter strings vibrated more rapidly than longer ones, and the more rapid vibration seemed to produce the shriller sound. By 400 BC, Archytas of Tarentum, 420 to 360 BC, a member of the Pythagorean school, was suggesting that sound was produced by the striking together of bodies, swift motion producing high pitch and slow motion producing low pitch. By about 350 BC, Aristotle was pointing out that the vibrating string was striking the air, and that the portion of the air which was struck must in turn be moved to strike a neighboring portion, which in turn struck the next portion, and so on. To Aristotle, then, it seemed that air was necessary as a medium through which sound was conducted, and he reasoned that sound would not be conducted through a vacuum. In this, Aristotle was correct. Since in rapid rhythm, a vibrating string strikes the air not once, but many times, not one blow, but a long series of blows must be conducted by the air. The Roman engineer Marcus Vitruvius Pollio, writing in the 1st century BC, suggested that the air did not merely move, but vibrated, and that it did so in response to the vibrations of the string. It was these air vibrations, he held, that were heard as sound. Finally, about 500 AD, the Roman philosopher Anicius Manilius Servinus Boethius 480 to 524, made this specific comparison of the conduction of sound through the air with the waves produced in calm water by a dropping pebble. While this analogy has its value, and while water waves can be used to this day, and are so used in this book, for instance, to serve as a preliminary to a consideration of sound waves, there are nevertheless important differences between water waves and sound waves. Transverse waves, such as water waves, can appear only under certain conditions. Such waves represent conditions in which one section of a body moves sideways with respect to another, and then reverses that motion. You can provide a transverse wave in a tall stack of cards by moving each card sideways by the proper amount. Such a sideways motion is produced by a type of force called a shear. For such a force to result in a transverse wave, however, the force producing the shear must be countered by another force that brings the portions of the body back into line. Within a solid, for instance, a blow may cause a portion of the substance to move sideways with respect to a neighboring portion. The strong cohesive forces between the molecules of a solid, which tend to keep each molecule in place, act to bring the displaced section back. It shoots back, overshoots the mark, shoots back again, overshoots the mark again, and so on. The resulting vibration is propagated just as the waves on a water surface are, and as a result it is possible to have transverse waves through the body of a solid. The cohesive forces in liquids and gases are, however, very weak in comparison to those in solids, and do not serve to restore a shear. If a portion of water or air is shifted sideways with respect to a neighboring portion, additional water or air will simply flow into the region left empty by the shifting portion, and the new arrangement of portions will remain. There are therefore no transverse waves through the body of a fluid. To be sure, transverse waves will travel over the horizontal upper surface of liquids, for there we have the special case of an outside force, gravity, resisting the up and down shear. Within the body of the liquid, gravity cannot be counted upon to do this work, for each fragment of water is buoyed up by the surrounding water. Since the density of each bit of water is equal to the density of the surrounding water, each bit of water has a weight of 0, see page 124, and does not respond to gravity. If a portion of water within the body of the liquid is raised by a shear, it remains in the new position in spite of gravity. Since transverse waves are confined to the surface of a fluid, and since gases have no definite volume and therefore no definite surface, it follows that transverse waves cannot be transmitted by gases under any condition. Consequently, if sound is transmitted through the air as a wave form, as all the evidence indicates it must be, the wave form cannot be transverse. A logical alternative is that it consists of periodic compressions and rarefactions. Consider the vibrations of a tuning fork, for instance. The prong of a tuning fork moves right, left, in a rapid periodic motion. As it moves right, the molecules of the air lying immediately to the right are pushed together, forming a small volume of compression. The pressure within the compressed volume is greater than the neighboring volume of normal air. The molecules in the compressed volume spring apart and push against the neighboring volume, compressing it. The neighboring volume compresses its neighbor as it springs apart, and so on. Thus, a volume of compression is propagated outward in all directions, forming an expanding sphere about the source of the disturbance, just as the crest of a water wave forms an expanding circle about its source of disturbance. The atmosphere is a three-dimensional medium, the surface of the water a two-dimensional one, which is why we have an expanding sphere in one case, an expanding circle in the other. Meanwhile, the prong of the tuning fork, having moved to the right and set off an expanding volume of compression, next moves to the left. More room is made to the right of the prong, and the air in the immediate volume expands and becomes relatively rarefied. Pressure is higher in the neighboring unrarefied air, which therefore pushes into the rarefied volume and is itself rarefied in the process. In this way, a volume of rarefaction expands outward on the heels of the volume of compression. Again, the prong of the tuning fork moves right, then left, then right, so that volumes of compression and volumes of rarefaction follow each other outward in rapid alternation for as long as the prong continues to vibrate. Each period of the prong, one movement back and forth, sets up compression-rarefaction combination. In these waves of alternate compression and rarefaction, the individual molecules of air move in one direction when compressed, then in the reverse direction when rarefied. The volumes of compression and rarefaction move outward and are propagated in a direction parallel to the back and forth motion of the molecules. Such a wave, in which the particles move parallel to the propagation rather than perpendicular to it, is a longitudinal wave, or a compression wave. Longitudinal waves are harder to picture and grasp than are transverse waves, for there are no examples out of common experience that we can draw on to illustrate the former in the way we used water waves to illustrate the latter. Nevertheless, having gone into some detail about transverse waves, we can deal with longitudinal waves by analogy. The points of maximum compression are analogous to the crests in transverse waves, and the points of maximum rarefaction to the troughs. In between, there are areas where pressure is momentarily normal, and these correspond to the nodes. The distance between points of maximum compression, or between points of maximum rarefaction, is the wavelength of the longitudinal wave. The number of points of maximum compression or of maximum rarefaction passing a given position in 1 second is the frequency of the longitudinal wave. Since the molecules of liquids and solids as well as those of gases evolve a restoring counterforce when compressed, longitudinal waves can be carried through gases, liquids, and solids. Sound waves in particular are carried by water and by steel, as well as by air. Waves produced in the body of the earth by the vibrations induced by earthquakes are of both varieties, transverse and longitudinal. Both can be transmitted by the solid matter of the earth, but it was found that when the waves penetrated a certain depth below the earth's surface, only the longitudinal ones could continue onward, while the transverse waves were stopped suddenly and entirely. It was from this that geologists were able to deduce that the earth contains a liquid core, and to measure its diameter with considerable accuracy. Sound waves, however, cannot be conducted in the complete absence of molecules. If an electric bell is suspended in a bell jar and set to ring, it will be heard through the glass, which can carry sound waves. If the bell jar is gradually evacuated, the sound of the bell will become fainter and will eventually fade out altogether. The clapper may continue to strike the bell furiously, and the bell may even be seen to vibrate, but no longitudinal waves can be set up among the molecules of an air that does not exist. As a result, sound will not be heard. It is frequently stated that the moon, which lacks an atmosphere, is a soundless world. However, sound can be transmitted through the moon's crust, and an astronaut may hear a distant explosion if he makes the proper contact with the moon's surface. Loudness. Suppose we consider a sound wave in which the succession of compressions and rarefactions are regular. This would be analogous to a transverse wave that had the form of a regular sine curve. Such a sound wave is heard by us as a steady musical note and is produced by a tuning fork. Indeed, if a pin is attached to the prong of a tuning fork in such a way that it makes contact with a roll of paper being moved at constant velocity in a direction at right angles to the vibration of the prong, a sine wave will be produced. A tuning fork may produce sounds that differ in loudness. If it is struck lightly, it will emit a soft sound. If struck more heavily, it will emit a sound which our ear will detect as identical with the first, except for being louder. The lightly struck tuning fork will move back and forth over a comparatively small arc. The more heavily struck one will move back and forth over a larger arc. As is to be expected of simple harmonic motion, the two movements will involve an identical period despite the differences in amplitude. So either way, the same number of volumes of compression and rarefactions are set up per second. The frequency of the sound produced is, therefore, the same in either case. However, the more heavily struck tuning fork, moving in the larger arc, compresses the air more violently. Therefore, a louder note differs from a softer note in that the compressed volumes of the former are more compressed, and the rarefied volumes more rarefied. The greater difference in extent of compression in a longitudinal wave is analogous to a greater amplitude in a transverse wave. This can be easily visualized if we think again of the tuning fork with the pin attached. A gently vibrating prong would mark off a sine curve of small amplitude. One vibrating through a greater arc as a result of a heavier blow would mark off a sine curve of greater amplitude. To compress air against the resistance of its pressure requires energy, and the compressed air contains a store of energy that it can expend by expanding and pushing whatever is in the neighborhood. For this reason, sound waves can be considered a form of energy. The more the air is compressed, the more energy it contains and can expend. Another way of looking at it is to consider that the vibrating tuning fork has kinetic energy that it expended in compressing air. If the prong swings through a greater arc, but completes its period in the same time, it moves at a greater average velocity, and has more kinetic energy that it can expend in compressing air. Whichever way we look at it, we can come to the conclusion that loudness is a matter of quantity of energy, and that a loud sound contains more energy than a soft one. The loudness or intensity of sound is measured in terms of the quantity of energy passing each second through 1 square centimeter of area, the area being perpendicular to the direction of propagation of the sound. Energy expended per unit time is power, and the amount of power involved in sound is very small. To indicate just how small, let's reconsider some units of power. A watt is the MKS unit of power, and is equal to 1 joule per second. We are familiar with watts in connection with light bulbs. We all know that a light with a power of 75 watts is none too bright for reading purposes, and that one with as little power as 40 watts is rather dim. Even a night light, just bright enough to dispel the worst of the shadows and enable us to get to the bathroom at night without tripping over the furniture, has a power of 1/4 watt. A microwatt is 1/1,000,000th of a watt, so that such a nightlight has a power of 250,000 microwatts. In comparison with that, ordinary conversational sounds carry a power of about 1,000 microwatts, and low sounds sink down to bare fractions of a microwatt. The ear detects differences in loudness by ratios of power rather than by actual differences. Thus, a 2,000 microwatt sound will seem a certain amount louder than a 1,000 microwatt sound, but a 3,000 microwatt sound will not appear louder by as much again. It takes a 4,000 microwatt sound to seem louder by as much as a 2,000 microwatt sound is louder than a 1,000 microwatt sound. To get a sound that is as much louder still than a 4,000 microwatt sound, we must rise to an 8,000 microwatt sound. The ratios 2,000 to 1,000, 4,000 to 2,000, and 8,000 to 4,000 are all equal, even though the differences are not. And it is by ratios that the ear judges. This means that the ear acts not by the power of a sound, but by the logarithm of that power. When one sound carries 10 times the power of a second sound, the ratio of the power of the first to that of the second is 10, and the logarithm of that ratio is 1. The difference in sound intensity is then said to be 1 Bell, so named in honor of Alexander Graham Bell, 1847 to 1922, who studied the physics of sound and invented the telephone. Similarly, if one sound is 100 times as powerful as another, it is 2 bells louder. And if it is 1,000 times as powerful, it is 3 bells louder, and so on. This kind of unit imitates the logarithmic working of the ear. The bell is rather too large a unit for convenience. A tenth of a bell is a decibel. One sound is a decibel louder than another sound when the first is 1.26 times as powerful as the second, for the logarithm of 1.26 is just about 0.1. Because of the same amount of energy represented by even loud sounds, sound energy is not something we are usually aware of. The energy of a roll of thunder may be sufficient to cause objects to vibrate noticeably. The telephone is an example of the manner in which human ingenuity has managed to usefully convert sound energy into electrical energy and back to sound energy. For the most part, however, the sounds that continually surround us, whether created by human beings, by other forms of life, or by inanimate surroundings, simply fade out and are converted into heat. If sound remained unconverted into other forms of energy, we could easily see how the loudness of sound would fall off with distance from the source. The sound wave moves outward as an expanding sphere from the source, and the total power, represented by each sound wave, spreads out over that surface. The surface of a sphere is equal to 4 times pi times the radius squared, where r is the radius of the sphere. That is, the distance from the source. If the distance from the center is tripled, the surface area is increased 9-fold, and only 1/9 as much power passes through any square centimeter of the surface. The intensity of sound would then be expected to vary inversely as the square of the distance from the source. This is how the intensity of gravitational attraction falls off, for instance. However, gravity is not absorbed by matter, whereas sound is easily absorbed by most of the objects with which it makes contact, even by the air itself. As a result, sound falls off more rapidly than one would expect.